So, do prediction errors usually increase or decrease with more flexible models? Now, this is the figure taken from the book, An Introduction to Statistical Learning, which is recommended for this course. And as you can see here, black line represents the true population function. So this captures the true data generating process. And these different colored lines, orange, blue, and green, are all candidate approximations based on a sample at different flexibility levels. So the right plot shows how mean squared error changes with the model flexibility. So for example, this is the mean squared error that was obtained on the training sample. And as you can see, it always decreases with the model flexibility. This is something that you know already from the econometrics. Now, out of sample or validation or test mean squared error first decreases with model flexibility, but then starts to increase. So, for example, in this example, the medium flexibility model wins. But in this example, a more linear model would win. Why? Because the true data generating process is also somewhat close to a straight line. Whereas here, the true data generating process is quite non-linear, which in result will lead us to choose a more flexible model. So the question is, why does the out-of-sample mean squared error have this U shape? And the answer is because of bias-variance trade-off. So if we decompose mathematically the expected out-of-sample mean squared error, we will get three components. First component is variance, or the degree to which the shape of the model that you train varies in different samples. For example, here I fit exactly the same polynomial model, but you see the shape will change every time in different new sample, whereas the samples are produced by the same data generating process. So the shapes of the same model will vary depending on the sample. So the second term basically captures errors that we inevitably get from simplifying a complex data generating process by some simpler model. And the final part is the irreducible error. There is, of course, some other factors that lead Y to vary in our sample or in general in data generating process, and it has nothing to do with X, and that is why it's called irreducible error. This variance that comes from other external factors, we cannot do anything about it. But we can do something about variance and bias. And model flexibility directly affects variance and bias. And that's why we call it variance and bias trade-off, because more flexible models will allow us to have lower bias, but will lead to a higher variance. If we plot different models, different statistical machine learning models into this kind of graph where we vary them by how flexible they are or how interpretable they are, you would see that the subset selection or lasso would be called the least flexible ones, followed by least squares, generalized additive models, trees. Then you have bagging, boosting, support vector machines, and I put here also neural networks. And this is the graph also taken from the ISLR book. The different models will have different levels of flexibility, and of course for tasks like image recognition, this is a perfect example of a highly nonlinear data generating process, and this is the reason why more flexible models really outperform all less flexible models here. For example, deep learning does do better than support vector machines for these tasks. And I would like to finish this video by citing Alex Pejsehovic, who is a leading economist at AI division of Facebook. He said, "Tried fancy ML, spent many hours, regression better." As you can see, in many cases you do not need a bazooka to kill a mouse.